Hello everyone. Today I'm going to give a talk about recent progress of PandaX-4T dark matter search experiment on behalf of PandaX collaboration. Throughout the last century, dark matter's gravitational effects have been observed in various spatial and time scales in the universe, from galactic rotation curve measurement to observation of bullet clusters collision. And finally, cosmic microwave background survey gives the dark matter consists of approximately 27% of mass energy of the universe. However, we can say it is a common knowledge that dark matter exists in the universe. We have no idea what its essence is. Most scientists believe that it is a kind of beyond standard model particle, which could have very weak interaction with baryonic matter. PandaX photon experiment is such a dark matter search experiment, utilizing high-sensitive underground detector with ultra-raw background to search for dark matter's direct interaction with target matter. Our collaboration consists of about 70 scientists, including 17 institutes. The detector technique we use is dual-phase xenotime projection chamber (TPC). TPC usually is a cylindrical volume and consists of three layers of electrodes: cathode, gate, and anode. It is called dual phase because the liquid surface must be placed in between the gate and anode. When an incoming particle interacts with target material inside the sensitive volume, it leaves certain amount of ions and electrons. Some of them recombine instantaneously and create scintillation lights, which are detected by the PMTs instrumented at top and bottom of TPC. We call this signal S1. The remaining electrons drift to the liquid surface under the drift field between the gate and the cathode, and get extracted from the liquid into the gas under a stronger field between the anode and the gate. The electron travels in the gas, exciting the xenon atoms on the way and also creates some scintillation lights. We call these S2 signals. And S2 signal is proportional to the electron number drifted. On the waveform level, the S1 and S2 have different width due to their distinct production mechanisms and can be easily distinguished. TPC is widely used in dark matter direct search and has currently best sensitivity to WIMP search with mass larger than 10 GeV. First, it has a large monolithic target, which makes it relatively easy to scale up to large detector. And TPC has very good 3D position reconstruction capability to reject background by fiducial visualization and single multiple scatter identification. The C position or the depths can be reconstructed using the time difference between S1 and S2 signals, and the XY position or the transverse position can be reconstructed using the pattern of the S2 on PMTs, especially on top PMTs. In addition, TPC also can have very good background discrimination power using the ratio of S2 and S1. In xenon, most background such as gamma rays and beta, interacts with the shell electrons and deposit energy through electronic recall, different from the WIMP, which hypothetically deposit energy through nuclear recall. The ionization densities of the two recall types are different, leading to a different S2 over S1 ratio, which is used for the discrimination. At last, the TPC has as a calorimeter, has very low threshold. It can see signals with a couple of photons or a single electron, guaranteeing its low threshold. PandaX photon detector is the third dark matter detector of PandaX. PandaX collaboration was formed in 2009 and started design and construction of PandaX Phase 1. PandaX Phase 1 uses a detector with only 120 kilograms of xenon. PandaX-1 started operation in 2014, and then quickly the detector was upgraded to a 580 kilogram detector called PandaX Phase 2, which operated during 2016 and 2018 and obtained very good result. PandaX Photon now is moved to a new lab with all systems upgraded. PandaX experiment series are located in China Jinping Laboratory, which is near Xicheng City in Sichuan province. The lab is in the middle of a long tunnel and has a rock overburden of 2,400 meters, which is the deepest in the world. The first two phases of PandaX experiment were conducted in CGPO-1 lab. In 2019, PandaX experiment moved to a larger home, CGPL2 lab. We are now using the B2 hole having a space of 65 meters in length and 14 meters in width and height. Here shows you a schematic of the B2 hole. In the entry, we have the pure water system and the gas xenon storage system. And in the center of the hole, maybe it is not showing the plot, but we have a large clean room hosting the cryogenic system, the purification system, and the data taking system inside. Behind the clean room, in the innermost part of the hole, stands the 10-meter high distillation tower for krypton and radon removal. Below the clean room is the water tank with 900 tons of pure water as passive shielding. In the middle of the tank is the detector's cryostat. PandaX-4T uses a TPC with 1.2 meter in height and diameter, with 169 3-inch PMTs at the top and 199 PMTs at the bottom, hosting about 3.7 tons of xenon in the sensitive volume. A short list of PandaX-4T's milestones. In April 2nd, 2018, we got approval from the CGPL Management Committee that we can move in and start construction, mainly in the water tank in B2 hole. In April of 2019, the construction of infrastructure was completed. From then on, the detector installation and offline distillation of xenon was started. In March of 2020, the offline distillation was finished, and in May, the detector installation finished. Testing and adjustment of all systems were then started. Finally, in November 2020, all systems were ready, and we started commissioning data taking until April 2021. In next few slides, we will talk about the results of dark matter search using these commissioning data. But first, let's see some photos of the TPC when it was installed. And here is the last photo of the detector's cryostat before water filling. During the commissioning, the detector's condition was mostly stable. We adjusted the purification speed and the detector's pressure several times. The pressure and temperature variation in the stable running period are within 0.5% and 0.1 Kelvin, respectively. The purification speed was at about 110 standard liters per minute for most of the running time. During the commissioning, there's discharge actually happening time by time. Most adjustments of detector condition were made to avoid the discharge. Therefore, we divided data into 5 data sets according to their gate and cathode voltages shown here. The longest 2 data sets, set 4 and set 5, are with 16 kilovolts on cathode and 5 kilovolts on gate, corresponding to a nominal drift field of about 92 volt per centimeter and electron lifetime efficiency, electron extraction efficiency at liquid surface of about 90%. The purity of the liquid xenon was also very low during the commissioning run. The electron lifetime was mostly above 800 microseconds. The total data taking period is 95 calendar days. After the data selection and the discharging file removal, 86 days remained. The efficiency was estimated using electronic recoil and nuclear recoil calibration data modeled on S1 and S2 separately. In the right plot shows the efficiency as a function of modeled nuclear recoil energy. The efficiency starts to drop around 10 keV, and the maximal efficiency is about 78%. And in this table, it shows our background components in final statistical inference. The major background actually comes from a component we didn't expect, the radic treated meson from xenon used in PandaX-2. So in the end of PandaX-2, a calibration campaign was performed using treated meson, and apparently there's some small amount of this meson still remained in the xenon, which is injected in PandaX-4T now. So from the final statistical inference, the best fit shows 532 events are from this tritium methane. Besides the tritium methane, we expect the radium-222 outgassing from the material, krypton-85 impurity in the xenon, and the radioactivity in the material also contribute to the low energy electronic recall background. The spectrum should be flat. We expect 492 events come from this flat, so-called the flat ER background in 86 days of commissioning data. Besides these two, there are also xenon-127 decays, neutrons, surface background, accidental pileup, and the solar boron-8 neutrino also contribute to the background. Below the NR median on the S2 over S1 space, which is the region in our detector with the highest signal to background ratio, we expect 9.8 events, background events, most of which are from the electronic recall. More details of the background components can be found in Ito's talk. Based on the background model and the spatial distribution of some backgrounds, mainly the neutron and the material background, which have the strong spatial dependence, the fiducial volume was optimized using a figure of merit approach. The final total fiducial mass is determined to be 2.67 tons. And our final search window of S1 is between 2 and 135 photoelectron. S2 between 80 and 20,000 photoelectron. And 1,058 events were found in 86 days of commissioning data, and 6 leakage below the NR median were found. These 6 events do not have features in their position, which is consistent with our prediction that the uniformly distributed electronic recall is the dominant background component. Our final statistic inference was performed on S2 over S1 spatial, but here I shows you a projection on the S1 space. The data model matching is pretty good with a goodness of fit p-value calculated to be 0.58. And here is a likelihood component of these 6 leakage events, and surely they are mostly consistent with the background prediction. Most of them are very likely from the electronic recall leakage. So we finally used 0.63 ton-year exposure of the commissioning data to give a constraint on spin-independent elastically scattering WIMP cross-section. WIMP nucleon cross-section. The sensitivity has been improved by a factor of 2.9 compared to previous PandaX-2 results at WIMP mass of 30 GeV. And due to the statistical downward fluctuation of PandaX-4T, the upper limit is almost 1.24 times better than previous best results from xenon-1T. Summary, PandaX-4T has successfully completed its commissioning run with a 0.63 ton-year exposure. PandaX-4T has produced the strongest WIMP nuclear interaction strain. This also demonstrates the physics potential of a highly sensitive multi-ton liquid xenon detector. However, during the commissioning, we also met some problem, especially the tritium methane background. So PandaX-4T is now performing an offline tritium methane removal campaign aiming to reduce this electronic recall background by at least a factor of 2. Also in parallel, the collaboration is developing the plan for the next generation multi-10-ton experiment at the CGPL as well. So that's all for my today's talk. Thank you very much for listening.